So welcome back, everybody, and welcome to this next session on the security stream. It gives me great pleasure to welcome Isha Powers back to GSE. If you remember at the time when we were allowed to have the conference in person, which was like 2 years ago, Isha came and did a presentation around crypto, and she was subjected to recording because we remember we were recording some of the sessions. So welcome back, Isha. So this is session 1AK for the purpose of feedback. I don't really have much to say other than welcome everybody. Do leave your questions and comments in the chat, and we'll pick those up at a suitable point. And then towards the end, if we have time, I'll unmute line so you can throw questions at Isha. So without further ado, welcome back, Isha. The stage is yours.
Thank you so much. Are you able to hear and see me okay?
Yes, perfectly.
Awesome. So hello, everyone. Thank you for the great intro, Jamie. My name is Isha Shireen Powers. I'm an IBMer, as you can see there. My area of expertise is cryptography. Most of you have probably seen me at like videos, or maybe you've seen me at some of the other sessions and conferences. I'm a huge crypto nerd. It's definitely my passion and my area of expertise. So I've spent probably about the last 17 years or so at IBM, most of that, of course, in the cryptography area, working on like the z/OS platform, and also engaging with the teams across the other areas too, like Linux and ZVM, the services and solutions in all different areas. So you can kind of see me more as an architect and someone who works really closely with a lot of different areas of cryptography. So in this session today, hopefully you're going to enjoy this. This is not just me talking to you. This will be me talking to you and also showing you some really cool things that you can do. So you can kind of stay along this lines of trusting no one. How do you ensure your data is protected, even if your data leaves your environment? Now, I love questions, so please ask questions as we go, and I will try to answer those as we go through the session. And if there's any question that maybe I can't answer, then I have great colleagues, and I can reach out to them, and we can get you answers for those too. So first, to everybody in the chat, definitely hello. Feel free to say hello to everyone there. If you're joining us from, like, maybe you're in the US, or maybe you're in the UK, or you're in Germany or Australia, or any other time, definitely let us know and say hi there too. And hope you guys enjoy the session. Okay, so of course, make sure you guys have probably seen this many times about the charity raffle and participating. It'd be great if you can participate in the raffle. Oh, I see Donna there from Minneapolis. Awesome. I actually grew up in the Midwest, in the Chicago area, though currently I'm in Los Angeles. Okay, so let's go ahead and get started. So I will admit to you guys, I've been wanting to use this picture forever. If any of you remember, there was a show called The X-Files that came out back probably when I was a teenager, and one of them, it was Fox Mulder, who was always super paranoid guy. And so I always like the idea of this trust no one. What the idea is, when you're a security person or a cryptography person, you're always considering like, who can you trust? And you're not thinking about, just like, at the outside world, right, protecting the perimeter, but you're also thinking even who can you trust in your own environment. And so you have many different layers of security and different technologies that you can deploy to make sure your data is protected from different attacks, from wherever they come, outside attacks, inside attacks, making sure people have just enough control to do what they need to do, but not too much. And so it's an interesting balance as a security professional, as an architect or an analyst, in trying to make sure that your data remains protected. And so essentially the mindset that we kind of go into this as is trust no one. You never know who that person is who may want to take your data. Should you trust a third-party vendor? Should you trust your storage administrator? Should you trust a contractor? Like, who should have access to sensitive data? And so we're going to dig into that a little bit today during this session. So many of you may have seen this chart. What we have looked at over the last probably 4 years or so is this concept of pervasive encryption, and how you can use encryption in many different ways and layered on top of one another And the idea is that you want to prevent breaches, and you want to, be able to comply with different regulations. So there are regulations that are, some that are international, like the Payment Card Industry Data Security Standard. And there may be some that are unique to Europe, like GDPR. There may be some unique to the US, like the Federal Information Processing Standard. And with these different regulations, they indicate what you can or cannot have um, in your system, in your environment, in your enterprise. They indicate which algorithms you can use. They let you know which, how your user ID should be protected. How should your passwords be protected? What kind of passwords are you allowed? So they kind of dictate different rules so that they can ensure that data is protected. Now, even beyond the compliance reasons, which is probably one of the biggest drivers for security, I will say, is compliance, because you don't want the fines. You don't want to be in the news because, GDPR, they fined you because, you weren't compliant. But also most of us, at our heart, we're security people. And so we want our systems to be secure. And so our goal is to, keep the bad guys out or keep the attackers out and make sure that the data is safe. And so those are some reasons that we also want to make sure that data is protected. And using encryption is a really, really great way to do that. Now, there's not saying encryption is the only technology. Now, think about multi-factor authentication is really awesome. I'm sure you've heard about other technologies. Earlier this week, you're going to hear about more, tomorrow, you're going to hear about more next week. But there's a lot of different technologies that you can use and you can put together to ensure your data is protected wherever your data may be. So let's talk a little bit about cryptography. And this is just a quick refresher on crypto. So y'all know, so crypto basically is the practice and study of techniques for secure communication in the presence of third parties, AKA adversaries. And with that, one of the really important things to think about with encryption and cryptography in general is it's not security by obscurity. It's not, hey, if I'm so small, nobody can find me. It's, oh, well, what I'm going to do is I'm going to put my data, I'm going to put my information, I'm going to put everything out there, and I'm going to give you information about it. And I'm going to say, well, even with that information, you still can attack or you cannot get to the sensitive data. Let me explain that a little bit further. So let's say you have a box and you have, some really super sensitive information. So you take that sensitive information, and what you can do is you can put that sensitive information, you put that in that box, and then you take that box and you put it in a room full of people. So you can have 100 or 1,000 people in the room, and you put the box there, and it has, this, sensitive information contained within it. And you tell that room of people, go ahead, get to the sensitive data. And they're like exploring the box and they're looking at it and they're trying to figure out, well, how do we get this open? Is it a puzzle? How do we figure this out? And then you say, okay, well, let me make it a little easier for you. Let me give you the specification for how the box is created. And so they get the box, and they also get a detailed document that describes how that box works. And so you give them the box, you give them the detailed description, and they say, okay, now you go try to break this. And they're still tinkering, reading, trying to come up with these intelligent ways of getting into that box. And they come up empty-handed. They cannot get to the sensitive data. And you say, well, why is that the case? If the algorithm for how the box is created is public, and we give you the box, well, there's additional secret information, which in our case, of encryption is a cryptographic key. And unless you have that cryptographic key, you're not getting within that box. So cryptography, the real idea with cryptography is, yes, we have this sensitive information, lock it up in this box, AKA encrypt it, put it out there in the world. And even though it's put out there for you to have, and we have all of the standardized algorithms like data encryption standard, AES, the advanced encryption standard, or if you like the new stuff, dilithium and all of the new quantum safe. Those standards, those things are published in a way that you can look at them and review them, but you still can't get into that box. And that's the value of cryptography and encryption specifically. So with cryptography, there are different aspects of security that can be covered by cryptography. So it's not just all about encryption. You can also do things like digital certificates. You can do things like hashing and signatures. So, and those things are different means if you're, applying cryptography in different ways to, protect data. Now, in some cases, you may not be protecting. So like with encrypt, decrypt, you're trying to protect someone from seeing the data. When it comes to like hashes, a hash is really just a proof that somebody hasn't tampered with the data. So it's really an integrity check. It's, did somebody change the data in any way? When you create a hash of a piece of data, essentially, if even one bit changes in the original data, you're going to get a completely different hash. And so with that, so you kind of know with that side of it, in hashing, that you know that that data hasn't changed. Now, it's great, of course, if you have a hash and you know that the data hasn't changed. That's wonderful to know. But also, what happens if you want to ensure that the data came from the right person? Yeah, you may have a document that somebody sent you. The document may not be secret. It could be something anybody can send. But you just want to make sure that it's integrity. Nobody went in and changed some bits and bytes. You want to make sure that it came from the person you thought it was. But then you do a signature, right, where you sign the hash. You hash it and then you sign it. And then the person who wants to be able to look at that data, they can verify the data. So those are some of the basics, in terms of cryptography and things you can do. Let's kind of dig a little bit further into encryption, because we're talking about trust no one. We're talking about the extensive use of encryption. So let's dig into that a little bit more. So let's start with traditional encryption. So with traditional encryption, let's say we're looking at data in flight, right? We're sending data from one environment to another. So with traditional encryption, you can encrypt the data so that it remains encrypted over the network. So over that network transmission, wherever it might be going, whether it's going from the US to the UK, or whether it's going to South Africa or Australia, you can make sure that that data remains encrypted. And then when you need to actually use the data, so when the data actually reaches its target, then you need to actually decrypt it in order to use it. So let's see an example here. So let me see if I can turn on a laser pointer. Okay, hopefully you can see that okay. So with the laser pointer, so you can kind of see I have my system here. This is my laptop. I'm connected to the internet. And with that, I'm going to request a secure connection, for example, to Z System. Z System says, oh, got your connection. Let me go ahead and send you my server certificate that identifies, who I am as a server. And it has, the server's information, and it also specifically includes the server's public key. Now, with that public key, now the browser on the other side can say, hey, let me validate the certificate. Let me check the certificate authority, make sure everything is fine in terms of the signing. Okay, that's good. So now your browser says, okay, well, let me generate a session key. So it's just a symmetric key it's going to generate. And then it says, okay, well, that system has the session key. We need to communicate with the server. So we're going to encrypt that session key with the server's public key, send it over to the server. And now the server has the private key. It can decrypt that session key. And now both sides have the same session key. They can send back and forth messages to one another. So that's basic encryption. But notice on each one of those sides, anytime, the client has to send data over to the server, it's encrypting it. Anytime the server has to send it back, it has to encrypt it. But then on either side, they always have to decrypt in order to read the message. So at some point in time, the data is going to be in the clear, whether it's going to be on the server system or whether it's going to be on the client system. Now, in between, of course, it's completely encrypted. So no worries about the wire, or no worries about the wireless connection. But it's really when that data lands in its target destination, it's going to be, it needs to be decrypted so it can actually be used. So that's data in flight. Now let's look at data at rest. So data at rest, and I'm sure you may have seen this pyramid before for pervasive encryption. There's different levels and layers of encryption. And the idea, if you haven't seen this before, is that different types of encryption will protect you against different types of attacks. And they also provide different types of coverage, or at least different breadth of coverage. So at the bottom here, what you can see is disk level encryption. And the disk level encryption is the widest encryption. And I want to know why, because when you turn on disk encryption, how much encryption do you get? 100%. Everything is encrypted on that disk, which is awesome. Somebody goes in to your data center, they try to steal one of those disks, completely useless to them because that data is protected, it's encrypted. Now you go up a level to something like the data set level encryption. And I know Ceci is going to talk about data set level encryption, I think maybe next week. And with the data set level encryption, though, you can see that it's pretty wide, but not quite as wide as the disk level encryption. And that's by design, that's intentional, right? You're going to encrypt a lot of data sets with data set encryption very easily. You turn it on by policy. It's really, it's not as complex. Maybe the key management may cause you to be like, ah, but for the most part, when you're doing data set encryption, it's very, very easy to enable and to use. And it covers a lot of different data sets. So, and then the number of data sets and types of data sets are constantly expanding. And I'll let Ceci talk about that in her session. But the idea is as you go higher and higher and higher up that pyramid, you're going to have less and less coverage, potentially. And it's going to get more complicated. So this level encryption is very easy to turn on. Data set level encryption is also pretty easy to turn on. Database encryption, yeah, it's pretty easy to turn on, easy-ish to turn on. And one of the cool things with database encryption is that you actually get the encryption of the data in the memory buffers, which is awesome because you want to make sure that, even someone, if you have to send a dump of your DB2 data off to, a vendor, someone that needs to diagnose a problem, that means that your data that's in that database and those tables, which could be sensitive identification information, it could be credit card information. If it's in memory there, if you have encryption turned on, then that data is encrypted in memory. And even as they're diagnosing issues, you don't have to have any concerns about you sending sensitive data to third parties. Now, when you get to application encryption, which is at the top of the pyramid, this one is like super granular. You have so much control. You can encrypt 4 bytes, you can encrypt 4 terabytes. It's completely up to you how much data you decide to encrypt. But the complexity goes up pretty high, right? Because now you really have to understand encryption very well. You have to understand, the algorithms. You have to understand initialization vectors. You have to understand how do you string together these different cryptographic libraries into your applications. And so it requires skills and resources and maintenance and development and all those things, which I still think is awesome because I'm a developer. And so I think, coding is fun. But some people might not like it. And so they might decide, hey, well, let me do one of these other options because it's easier. But the idea is just to show you that there's these different types of encryption. And from our perspective here with Trust No one thing to call out though is that even though we're using traditional encryption here, when you actually want to use that data, what do you have to do? You have to decrypt it. You have to decrypt the data in order to use it. So it's not something that you can just, operate on the data while it's encrypted. This, you actually have to, when you want to use the data, you decrypt it, you use it, and then you can encrypt it again. But the data is going to be decrypted at some point. Okay, so I'll turn this off so it won't be so distracting. So this chart here, so some of you, so with this particular chart here, what we're looking at is the concept of data privacy and just trying to kind of nail that idea down. So we've talked about cryptography, what it is. We've talked about encryption. We've talked about traditional encryption, data in flight. We've talked about data at rest as well. Now we're looking at privacy. And what privacy really says is, yeah, we're protecting our data, right? You're going to protect your data, but there's some people that should have access to it in an environment and some that shouldn't. And you should have the ability to control who can or cannot view certain data within an environment, saying that you are authorized to that environment, but you still maybe shouldn't allow just anybody to see, your data. And so you can put controls in place, like for example, when you have your disk encryptor, now you have a control in place that even if your data center technician he has authority to be in the data center. But even your data center technician can't just walk off with one of your disk drives. Well, he could, but it won't be of any use to him because it's encrypted. And your storage administrator, yeah, they're supposed to go and, allocate data sets, look at storage, manage different, environments, making sure that data is where it needs to be. But they don't necessarily need to view what's in the data sets, right? They can manage, the data set, they can delete things, move things around and make sure that the storage is adequately managed, but they don't necessarily need to read social security numbers, identification numbers, payment card information. And so you can prevent that with something like data set encryption. And then you have your support person, whether it's IBM or otherwise, they're reading your dumps. You have run into some problem, you need to send a dump and that dump may contain sensitive data. And so you can use database encryption and now whoever looks at that dump cannot view the data in the clear, at least not the sensitive data. And now you can also eliminate Bob, right? You're a database administrator. So if you're encrypting at the application level, you encrypt the data before it even gets to the database, and that means your database administrator cannot view the data in the clear as well. So there's all these different things that you can do to ensure that only the right people can view the data, and that's really the concept of data privacy. You get to decide who sees the data and who doesn't. Now, what becomes interesting is let's say that you are the data controller. You are the person that owns the data. So you could be a bank, or you could be government, or you can be insurance. You can be from any of these different industries. And this is the data that you have that is under your protection. You control that data. But you may need to send that data elsewhere. You may need to ETL it to send it to a data processor, someone who maybe can do analytics on the data, or maybe there's some other analysis you can do on the data, or maybe there's some cool AI application. So there's different reasons that you might want to take the data in your platform and have it sent to a third party, or have some type of work being performed elsewhere. And you have to consider that if you have data that could be, whether it's a social security number, which I know is more of a US example, but take it with a grain of salt. There's equivalent for the other countries as well. Maybe it's healthcare information. It could be credit card numbers. That information may be contained in what you want to be analyzed. And so then your thought process would be, well, is that data processor, the person I'm sending this data to, are they going to protect the data as well as you do? So you've taken all of these steps with pervasive encryption. You have encrypted disks and data sets and databases and applications and over the wire, and you know exactly how your environment is set up perfectly for security. But do you have the same guarantees from the person that you're sending it to that they're going to protect the data just as well as you are? Maybe. You don't know. Now, of course, I'm going to flip the other side, right? Because I'm not here to beat up on the data processors at all. So let's say you're the data processor now. So you came up with this really cool application. It is awesome. You want the whole world to use it. You put it out there. Maybe it's a container application in the cloud, and everybody's going to be sending their data to you, right? They're going to be sending you all this data. And as the data processor now, you want to provide assurance to your clients, the people who are entrusting you with their data. And you want to say, yes, I am sure, 100% sure, yes, you can send me your data. I can operate on it, but I won't be able to see it. Even if someone were, an administrator in my environment were to, try to get in and access the data, they can't. Wouldn't that be really, really awesome? So it doesn't matter if it's a credit card number or healthcare information, they can send you their data. You can process it without having to worry about what the details are within the data. Sounds pretty cool. So whether you're on the data controller side, sending off your data, or whether you're the data processor who's receiving data, technology that can actually operate on encrypted data would be really awesome on both sides. So the idea is, what if you could unlock the value of sensitive data while preserving privacy? So ensuring that, the data that you are sending and sharing remains private, but they can still do the operations, they can still do the analytics and all of those types of operations. Okay, so let's talk a little bit about this concept of fully homomorphic encryption, how it works. So first of all, this was something that was pioneered by IBM Research. I take absolutely no credit for it. I am the messenger. I love crypto, as I said, so I can talk to you about it, but I take no credit for inventing or creating it. I think Craig Gentry, he has that honor. So we'll leave that in his hands, but I will tell you all about it because it is a really, really cool technology that you guys should be aware of. So the idea with fully homomorphic encryption is that it keeps the data encrypted at all times. So let's kind of go through these different steps so you can kind of get an idea of how this works. So step one. So the first step here is you have the data controller, right? So the data controller is the person who owns the data, who may need to send that data to a data processor. So the data controller is going to encrypt the data. So before the data leaves their environment, they're going to encrypt it. So they're going to take that plain text, convert it to ciphertext. It's unreadable by humans. They're going to use FHE to do this. Then they're going to send that data over to the data processor. The data processor in step two here is going to do computation on the encrypted data. So they're going to use fully homomorphic encryption. They're going to do, whether it's detecting financial transaction fraud, whether it's analyzing DNA. There's different things that they can do. But the idea is that, they're going to operate or perform analysis on the data without having to see the data in the clear. They have only received encrypted data. They do not have the clear data. So the clear data has not left the building. It has not left your system. Only the encrypted data. Now in step 3, now it's the data processor is going to send the results back over to the data controller. And even the results that are getting sent back to the data controller, they're all encrypted too. So only the data controller can actually decrypt the results and actually view the output of the results. So you have this whole process that essentially the data never leaves the data controller in the clear. And even the results, as they come back, the results are also encrypted, which is pretty cool. So let's take a little bit of a closer look here. And let me get my laser pointer again. Okay, so here you have your data controller on the left, and you have your data processor on the right. So you have your plain text data here. And what you're doing is you're going to run that through a fully homomorphic encryption engine. And that engine's going to encrypt that data. And the encrypted data is what gets sent over to the data processor. Now, the data processor can do the computation that it needs, the analysis, whatever it might be. And then the encrypted results get sent back to the data controller, who can decrypt it and view the output. So the data, the entire time that it lives, lives or resides in the data processor, is always encrypted. It's operated on while it's encrypted. So let's talk about some of the different use cases that you can use with this. So I mentioned some of these already in talking to you, so I'm sure these are familiar. So analytics, of course, so you can do analytics on encrypted data. So whether it's a third party, whether it's containers, whether it's a different line of business, they can do analytics. So one of the examples here is marketing, sensitive customer data. They're going to run a campaign. There's this really cool tool that does all this great marketing stuff. So they want to send the data, but they don't want them to share, or they don't want to have the risk of that data being lost or being breached. So you can use fully homomorphic encryption to ensure the data is protected before it even gets sent over to the application. The same thing, you can do encrypted search and data matching. And actually, I'm going to show you a demo where we're actually going to do some of that, where you can actually see the encrypted search and the data matching. You can do encrypted AI and machine learning, of course. I know artificial intelligence and machine learning is really big. So if there are AI-driven insights that you can get, so think of different types of data that might be available, that you can use that to make predictions and do inferencing. Another area where you can use fully homomorphic encryption is encrypted biometrics and behavior. So if you're trying to do user behavior analysis and trying to make decisions based on, they normally do this same process like every day, this 1, 2, 3 step. But on this particular day, they did something a little different. And based on that, anomaly in their behavior, then you can start to say, there could be a risk here. Let me do some kind of a nullification. Maybe this is not the norm kind of process. And there's different applications and different, could be something offered by a third party that can do those types of things, can do that type of analysis. And so you might want to send your data there for analysis. So there's all of these different applications and these places that you can send your data to perform different types of analysis. And the idea is that you can send them the encrypted data so that you can ensure that the data remains protected. And if you're on the data processor side, you can operate on the data while it's encrypted so that you can provide the assurance to your clients that you can't see the data and you can't view the sensitive data. Okay, so who is the intended audience for this? You might say, okay, data scientists, of course, right? We just talked about artificial intelligence. We talked about machine learning. We talked about biometrics and things like that. So anybody that's working with like a lot of data, they're looking at data, analyzing data, of course. Application developers, yes, you guys too. You're going to use this, right? Because you want to ensure that your data is protected. So, but what I really want to call out, and the whole purpose of this slide is, so like I said, you don't have to be a cryptography expert to use fully homomorphic encryption. Now, of course, you could be. There's no problem with being a crypto expert, but you don't have to be. It's really for anyone who wants to protect data, maintain its privacy, even as that data may go in different areas, and still be able to operate and do different things with that data. So I'll take away my X, right? Because yeah, you you can be a crypto expert and you can definitely use it, but yeah, you don't have to be. And in the big picture is yes, you can use this too. So whether you're a crypto expert, or whether you're someone in security, or whether you're an application developer, or you're a line of business owner and you're just looking for new ways to protect data, you can use this. And so part of what I want to show you is a demo of how do you actually use the fully homomorphic encryption toolkit, so that you can get started playing around and getting just a feel, getting a comfort level with fully homomorphic encryption. So before I do the demo, are there any questions in the chat before I fire up my demo? I don't see any yet, but if there are any.
No, I don't see anything neither, Isha. So
Mhm. So let me switch over to, this is a recorded demo because, you know how sometimes you try to do a live demo and then like everything goes haywire. So I recorded this last week. So you'll see this demo and it's about 15 minutes or so. And it'll just show you like the fully homomorphic encryption toolkit and how it works and how it looks. So let me bring that up. Let me share. Okay, and you should be able to see this video. Jamie, can you keep me honest? Are you able to see the video okay?
sure, yeah, I can see you. I can see you. A younger you.
Hello and welcome to the Fully
Thank
Homomorphic
you.
Encryption Toolkit demo. So the idea with this demo is I want to kind of explain a little bit more about fully homomorphic encryption and then show you how you can actually use it, right? It's great to hear and read about, new technologies and new capabilities, but it's another thing when you can actually play with it. So hopefully this is enough information where you can actually start to play with fully homomorphic encryption on your own systems and in your Docker environments. And it should be kind of fun to look at. So let's go ahead and get started. Okay, so where we're going to start is we're going to start by looking at just a real quick animation, which is a really nice way of demonstrating how fully homomorphic encryption is different from traditional encryption. So you've already heard from me about the idea that traditional encryption has to be decrypted before it's used, right? You're encrypting the data. You might store it somewhere, you might send it over the wire, but then when you actually need to use that data, you have to decrypt it to use it. Fully homomorphic encryption is different in that you're going to encrypt your data, you're going to send it elsewhere, and then that data can be operated on while it remains encrypted. And the results of those operations are sent back to the originator encrypted, and only the originator can actually decrypt the data and see the results. So what's nice about that is if you have your data controller environment where you control the data, you have to send it to a data processor, maybe in the cloud, maybe for analytics, they can do the processing on the data without seeing the data in the clear. And that gives you a bit of assurance and safety that your data is protected wherever it lives. So let's kind of look a little bit at the image here. So you see you start at your institution at the bottom. You have some data, it's encrypted, and it's sent into the cloud. And now you can see on the left, fully homomorphic encryption, where the data is operated on and while it's encrypted, versus on the right, where the data has to be decrypted to be used. Now with fully homomorphic encryption, the data is sent back to the financial institution in an encrypted form. And so only that institution is actually able to review the output and results. So that is another way of ensuring that your data is safe, even as you send it to different environments. Okay, so let's go ahead and let's look at this toolkit. So we're going to go out to GitHub and you can see the fully homomorphic toolkit for Linux. And here you can see lots of different files. All of this you're going to be really familiar with because we're going to actually, build an environment where we can run these different things. Now, when you scroll down and you look at the README, it'll give you more detail about the fully homomorphic encryption, about HE layers, the SDK, and information here. But where we're going to start is we're going to go and we're going to look at the toolkit README. So we're going to click on README toolkit here. Okay, so here we can see our toolkit, and so we can get more details about the toolkit and what it is and how it runs. And so the toolkit really is, it's packaged as Docker container, so it should be easy to run and available in different environments. It contains a few different things. It contains the homomorphic encryption library, HE Live, which you see there. It contains an integrated development environment in IDE, essentially that runs in a web browser. And it also includes a workspace and some example code that you can run immediately as well. It's supported on different variations of Linux. In our example, we're going to be using Ubuntu, but there's other versions that are available as well. Now, when you scroll down here, you can see more about supported configurations, how to run the toolkit, and we're going to go ahead and we're going to look at getting started with running the toolkit. So let's go there. Okay, so getting started with running this toolkit. So you have information here about prerequisites, right? You're going to need Git because you're going to clone the repository. You're going to need Docker because you're going to be using containers. And so that gives you an idea of what those prerequisites are. And then the steps to actually deploy and use the toolkit are pretty straightforward. Cloning the repository, fetching the images, running the toolkit. You can access the toolkit, and you will see this message when I demo as well, using the self-signed certificate. So just ignore that. If we had a CA signed certificate, then it would be happier, but just as an FYI. And then there's like notes about configuration and things like that. So all this information is available here in GitHub, so you have that for reference. And now what I'm going to do is I'm going to take you through some of these steps so that you can see just how it works and what it looks like. And one thing I do want to call out, just so Greg Boland, who is currently leading like the development effort, is just really, really great to work with. And if you have questions, he would be the person to ask. So thanks, Greg, for showing me this demo so that I can go and kind of get the word out to everyone else so that more people can use fully homomorphic encryption. Okay, so let's start here. So now I'm on my Linux system. And on this Linux system, what I want to do is I'm going to do a little bit of setup so that I can deploy the toolkit. So first thing here, I only have a couple of things in here, but I want to clone the repository. So we looked at the prereqs and you have to have Git. And so I'm going to do a Git clone of that repository. So cloning it, grabbing everything that I need. And now you can see I have the FHE toolkit Linux there. And so now what I want to do is I'm going to cd into that directory. And you can notice that some of these file names are all familiar because we just saw those when we looked at the GitHub repository. And so from here, what I'm going to go ahead is I'm going to run the toolkit. Oops. Let me recopy my command. And I'm just copying because I'm just too lazy to type. So just so you guys are aware. So it looks like FHE development is open for business. So we're going to go ahead, we're going to connect to my system, and we're going to look and go into kind of our workspace and our integrated development environment. So let's go back to our browser. So back to Google Chrome. And this is the image that I am running on. So let me go ahead. And like I said before, you're going to get this message. At least I'm getting this message because I'm using a self-signed certificate. But I know that it's okay. So I'm going to go ahead and proceed. So this takes me into my workspace. So you can see on the left-hand side, the FHE workspace. You can see on the side, like examples, which we're actually going to show and take you through. You saw a little pop-up there. I'm going to bring that up again. But the idea is that this is your workspace. This is your web browser version of your integrated development environment where we can look at code or we can do running of builds and things like that. So I'm going to kind of talk you through that. So we saw that pop up at the top of the screen. It's gone. Let me see if I can bring that up again. I need to select a kit. So in my environment, I am running on Linux on Z. And so I'm going to look for the S390X Linux. So I'm going to select that. And then what I'm going to do after I select that is I'm going to build my environment. So hit build there, you're going to see a pop-up where you're going to see the environment being built and created. And basically what we're doing here is we're building the environment because I want to be able to run some of the examples to show you, what it looks like. What does fully homomorphic encryption look like? What does it do? How does it work? And what's really cool is after we built this, and I'm going to show you some of the different examples that are here, then I can also show you the code that's behind it. So for those of you who want to dig in a little deeper or maybe write your own, applications, you can use that code there as an example or as a model. Okay, looks like the build finished, which is awesome. And so let's look at our first example. So to get to our first example, I want to play one of these. So let's see. I think the first one I'll do is I'm going to do the privacy preserving key value search. And so basically what this is going to demonstrate is the fact that you can encrypt some data. In this case, particularly, it's countries and the capitals of the countries. And what you can do there is it can actually do encrypted search, right? So the data is all completely encrypted, but I'm going to pass it some data that I'm going to put in the clear. It's going to encrypt that data. It's going to do a comparison, and it's going to see, hey, because you gave me this country, it's able to do a lookup and actually find the relevant capital. So let's go through and let's see how that works with homomorphic encryption. So let's click on number 1. You can see the terminal here running on my local machine. And so what I'm going to do here is I'm going to enter the name of the country. Now there are, of course, this is kind of like, if you go and actually look at the codes, you'll see there's like several countries you can choose from. So I'm a little biased. So the first one I'm going to choose is, of course, the United States. And so what it's doing is it's doing an encrypted search where it's not actually, decrypting the data before it search. It's actually doing the search on encrypted text using fully homomorphic encryption. So here, query result, Washington, DC. Awesome. But we can try a few different countries as well. So let's see, I have been to Germany. So let's go ahead and, actually, let me actually make sure I prompt. So let me recall the command so I can get my prompt. There we go. And now, Germany. What about the capital of Germany? I feel like I should have music in the background, but I don't have any music. Berlin, awesome. So we've got Berlin as the capital of Germany. I have also been to Denmark, so let's give that a try. Copenhagen, awesome, which is exactly where I went when I was in Denmark. And we'll get one more, and this is from my colleagues in Montpellier. So our country will be France. And you can see the capital there of France is Paris. So this is just one example of one, use case for a fully homomorphic encryption where you can do search on data without revealing, details about the data in the clear. So that's one cool example. So let me show another example. So another interesting example. A lot of the clients that I have worked with are in the financial sector, and they are, maybe have to comply with, payment card industry, data security standard, and other, industry regulations as well. And one of the concerns in the payment card industry is credit card fraud. And having the ability to detect credit card fraud. And so there's a lot of tools that are available to help with that fraud detection. And maybe those tools are available in the cloud, maybe available through a third-party vendor. But then there's the risk of, do you really want to send, your credit cards, these credit cards that your clients entrusted you with to the cloud, to this third party, so that they can, do the fraud detection. And wouldn't it be cool if you could send them just the encrypted values for the credit card information and system information, and have the fraud detection work on the encrypted value so that the credit cards themselves never have to appear in the clear. And that's something that you can do with fully homomorphic encryption. So let's take a look at this example. And this one does take a little bit longer to run because it's running multiple scenarios, but it's still kind of fun. So let's look at credit card fraud detection inferencing. And what I'm going to do is I'm going to play this one. And so what it's doing is it's saving the information. It's loading the model, it's encrypting the model, it's saving the encrypted model. The encrypted model is going to be available on the data processor. And we're going to be sending the encrypted data over to the data processor to be processed, right? The idea being that the data is only available in clear on the data controller in that host environment. And as the data, is being sent over to, that third party or to that data processor or to that analytics engine, that data is being sent over encrypted. The analytics engine has fully homomorphic encryption, so it knows how to operate on the data. And when it provides the results, the outcome of that fraud detection in this case, it can send that data back, encrypted, so that only the host, only the data controller can actually view the data in the clear. So it kind of absolves the data processor from, any, concerns about data breaches, because the data it receives is only in the clear and always in the clear. So in this example, you can kind of see on the screen here where it's doing, it's running through, it's checking whether or not, it can predict fraud or not. But the whole process of it, as it's doing, is just doing this all on encrypted data. So it's doing all of these operations essentially on data that remains, protected and only available to the host system. So that's a really, really cool example. And there's probably many, many more examples that you can create on your own for fully homomorphic encryption. But let me show you where you can see just how these examples work and what the code looks like. So if you look in your FHU workspace and you go to the left here, you can see examples. And for examples, let's say, for instance, we want to look at the world country database lookup, right, where we were putting in Germany and France, and we wanted to see, hey, what is the capital? So for those of you who are familiar with C, you can go and you can kind of look at the code here. You can see the includes, you can see, here how they're defining the different variables, the different arguments. When you scroll down, you can see the different functions that are being called, the different parameters and things like that. So I'm not going to go through in detail and explain every, parameter, every function in here. The idea is just to let you know that it is here and it's available so that you can take a look at it. And so you can get an idea of how you might build your own fully homomorphic encryption applications using the toolkit. And of course, there's more stuff here. Countries, these are some of the countries that we had to choose from. So it's a really, really great environment, really easy to use, a way for you to get started with fully homomorphic encryption. So what I'm going to do is I'm going to switch back to my deck here. That kind of serves as our demo. And then, of course, we want to make sure that you know that you are invited to play around with it. So definitely play around with fully homomorphic encryption. There's a lot of information that's available. It's very easy, as you can see from the demo, to download and run and use the different function in the toolkit. So I hope you will go ahead and take this as an invitation for you to get started. And I look forward to seeing what you can create. Thank you so much for listening to this demo. Bye, everyone.
And hopefully you can see me again. You can hear me back to normal.
Yes, for sure.
Awesome. I just want to check. So yeah, so you saw this slide. This is the year invited. So there's more information about how to, go to the Bluemix. You can kind of see the same animation that I just showed you. You can go to the GitHub page. You can see the code. You can build the environment for yourself, so you can get to start to play with it and see how it works or how you might be able to use it in your environment. We did have a great question in the comments about different use cases and environments where you can use fully homomorphic encryption. If you have additional use cases or things that you're like, I wonder if this works here. I wonder if this would work here. Please send me a note. I put my email in the chat. What I can do is I can engage with the technical team, and we can kind of evaluate and look at those use cases and see if they are covered. And if they are not covered, then we can add that to the list of things that, perhaps you would like to see covered in the future. So definitely reach out to me or put it in the chat if there's other use cases or scenarios that you can think of where you might want to use fully homomorphic encryption. So my last slide here is frequently asked questions. I've only gotten a couple, but I can keep adding this as I go. One question I got when I did this is, does the toolkit run only on IBM Z? So my example, of course, I'm running on a Z system, but no, answer is no, it doesn't just run on Z. I've also have like some of my colleagues, they've run it on their Windows laptop. Pretty much anything that can run like, the Docker containers, you can run the FHE toolkit. So, so you have like different options. Let's see, does it run only on Linux? Nope. Windows works too. It's pretty much anything that runs Docker containers. So you have different options for when you want to play around with the toolkit. One question I did hear recently was, how is this different from the HyperProtect data controller? That was a good question. And what is different with the HyperProtect data controllers? With that one, it gives you that control, it gives you the ability to do data privacy as your data is moving around. But when you want to use that data, you still have to decrypt it to use it, right? So you give authorization, right? And you can revoke that authorization at any time, but you still, when an operation needs to be performed on that third-party system, you still have to have that data decrypted. So it will be decrypted at some point, but you have the control to say, hey, well, I sent this data to this third party and I am a little concerned. And so you can revoke access like remotely without even having to do anything on their system. So the HyperProtect data controller gives you a whole lot of control, even in environments that are not your own. But from an encryption decryption perspective, you still at some point that data is going to have to be decrypted to be used because it's not using FHE. And I see a hand raise. I don't know how to unmute.
It's okay. Christian, you should be able to unmute your line now.
Hello, can you hear me?
Yes.
Okay, hello again.
Hello.
Sorry, Isha, it's just being me. I had a quick look at the GitHub, and looks like there is your entire source code there. Okay,
Yes.
In the light of the SolarWinds hack 2 years ago, how can you be sure that a bad actor is not switching something or swapping something?
Oh, with the source code. So yeah, so the source code there, that's all open source. So just like kind of any other GitHub thing. In terms of bad actors and whether or not they can manipulate, I guess it would be, let me think about like how that would work with a particular GitHub repository. The code, the algorithms itself, when it comes to the different, I'm trying to like think of like a good answer for that one. It's like I didn't have a connection to the SolarWinds hack and the detail that was involved in that particular case.
Well,
So
sorry to.
Oh, no, it's a great question. It's awesome to get stumped. Every once in a while, I definitely get stumped. So I think you got me on that one. So I may have to like do a little digging and kind of get back to you on that. Is there concern about the fact that the code is open source, and so someone might go change it, run it in their environment, and now they're able to get to sensitive data?
Exactly. You see, so technically, it's let's say if you want putting malware in the first block of a blockchain. So basically it will propagate technically. So this is what happened with SolarWinds. And that's why, so technically, let's say if I am a bad actor and I'm putting malware in there, more people using your code that has been modified by me, there's more infected computers, if you want, so less privacy or less encryption.
Yeah, and I can't confirm, like, and I won't even pretend to say whether I'm familiar with the review process that they have on the GitHub page and who's allowed to make changes to it and then republish it. So I imagine that there is a process because supply chain attacks is definitely something that's a big deal right now. So, but I'll have to, but on the specifics, I will have to get back to you on specifically how they're ensuring that the GitHub is protected and that no one can go in and make changes to it and then republish it out there as if it came from IBM and then use it in an attack.
Please do. Thank you very much. Thank you.
Yeah, thank you.
And Rob Van Hoboken. Hi, Rob. Puts an interesting comment in for you, Christian. He says all of the source code of Linux is in GitHub files too. Does this imply you should not use Linux? And you're a Linux user. Christian?
Yes, I am, but well, it's quite well protected. I have some defenses in place. So don't worry about me. I'm worrying more about the people out there.
Sure. Any more questions for Isha? You can unmute your line, folks, if you want. If you have a question, you want to ask a question directly. I find it, just while we're waiting, Isha, I find it fascinating, the whole, I can never pronounce it. I mean, homomorphic encryption.
It takes a lot of practice.
It takes a lot of practice. There is that, but yeah, it solves quite a lot of problems, doesn't it, with regards to the transmission of data, and very, very clever, I would say. I'm not a crypto guy at all, and I can barely spell it, but the way that you explained it, I think you explained it beautifully, actually, I have to say. Even I understood it as you were going through different use cases and things. So thank you very, very much for what you've done and taking the time to prepare your session. So before we close for the day, are there any additional questions? Don't be shy, folks.
Can I ask a question, Jamie?
And Lenny.
Hi, Aisha. The demonstration you gave, you showed where you are, unless I've misunderstood it, which is entirely possible, you've searched a database that was encrypted and you've looked for a specific value. It's not, it seems to me that you could have done that without using homomorphic encryption, because all you need to do is encrypt the argument and then search. The second point is that you must have decrypted the answer in order to present information to us anyway. So,
yeah, and it was in the clear when I typed it in, and then it didn't
exactly,
get the encryption, and it came back. Yep. Yeah,
so
part of the demo was the decryption, so you guys could see the answer.
Yes.
But generally speaking, it's under the data controller's control who does see it. So the data controller gets the data back encrypted, and then they can decrypt it for the people to see or for me to see in that particular application.
Okay, so it seems to me that there is some fairly complicated key management going on here. In order to access the data using fully homomorphic encryption, do we still have to supply a key?
You have to, yes. Yeah, you do have to have the key in order to do it. So, and I think that on the side of, on the decryption key, of course, is only on the side of the controller.
Right. And so is it a decryption? That's what I was trying to get at is it a decryption key, or is it a key that allows you to do homomorphic operations without decrypting it? In other words, simply having the key allows you to decrypt it anyway. If it allows you to decrypt it, the fact that you can operate on it homomorphically is good, but it seems to me it would be better if you had a key which only allowed the homomorphic encryption operations to take place and didn't allow you to decrypt it. Maybe I'm misunderstanding, but if you see what I mean, that if I can operate on the data, I want a key that allows me to operate on that data and do the things that maybe I need to do, but it doesn't. I want a separate key that allows me to decrypt the answers. So if I get a particular record out of a database, then I think the interpretation of that ought to be under a separate key, or that's how I'm feeling at the moment. Because if I need access to a key which can decrypt it, merely in order to do the homomorphic encryption, then that key must be in storage as well.
Yeah, so looking back at how this works with the data controller and data processor, let me see if I can turn the laser point. And I know I'm running over, I might be running over a little bit, but so you see how the key management is here too in the data controller, where you see the private key that's actually used for the encryption. and the public key being made available for the actual operation itself. But the private key here never leaves, essentially. So only the data controller can actually decrypt, or, you know, or even in this case, be able to encrypt the data. So on this side, the public key is what's available to the data processor.
Okay. I'll have to look at that more in more detail. Okay, fine. Thank you. I won't take up any more of your time because I know you're running
No
off.
worries.
It's all right. It's okay. Just been puzzling me.
Thanks, Larry. Any more questions for Isha? No? Okay, well, big round of applause for you, Isha. Thank you so much, and thanks for coming back to us. We'll have you back on air again at some point with us. But anyway, folks, please do leave your feedback for Isha. So this is session 1AK. So do that. Remember, it contributes to collecting your CPE points if you need them, enter into the prize draw, and of course we need feedback for the presenters and for GSE, so we'd be very grateful if you could do that. And also don't forget our charity. So up next, so we've got a 30-minute break, and then there is a keynote speech at 5 o'clock UK time, which is around infrastructure and application modernization on System Z. Sorry, I'm not saying Z, Isha, with Red Hat OpenShift. So do join that if you can. That's with Marcel Mitron from IBM. The security stream resumes tomorrow at midday UK time, and that's with Brian Childs. We're talking about Brian Childs from IBM, talking about the IBM ZOS authorized code scanner. So very much looking forward to that. But the conference does kick off at 9 o'clock. So although we're not starting until midday, other streams are running from 9 o'clock. So do take the opportunity to have a look around the agenda and see what else there takes your fancy, and join in. But yeah, from the security stream, thank you very much. And Isha, once again, thank you so much. Nice to have you back with us, and we'll see you again soon. All right, thanks everybody.